Hi everyone, this is Jiayang from the University of Melbourne. It is a great honor to be here to present our work, Amodal Intra-Class Instance Segmentation, Synthetic Datasets and Benchmark. Perceiving an entire object, even if it contains invisible segments, is a task that can be easily handled by human visual system, but it is still a challenge for computer vision. This capability, known as Amodal perception, is crucial for vision tasks that require reasoning about the occluding things to ensure reliability and safety, such as robot grasping system and auto-driving. With the end to mimic human Amodal perception, Amodal instance segmentation extends the traditional instance segmentation by additionally segmenting the occluded region of each instance. While considerable progress has been made in perceiving visible regions for computer vision, Amodal instance segmentation has received limited attention. We tackle a problem not addressed by the previous works, namely Amodal instance segmentation with heavy intra-class occlusion. How to handle the image with intra-class instance occlusion is one big challenge in Amodal instance segmentation. Due to the similarity between objects in the same class, intra-class instance segmentation becomes more challenged than inter-class instance segmentation, as class-specific features appear almost everywhere near the occlusion boundary. In particular, perceiving the complete range of the objects, including the hidden parts, can be extremely difficult for the machine when multiple objects of the same class partially overlap within the same region of interest. In practice, however, there are many things with density intra-class occlusion, such as warehouse and agricultural sites where robots work. In spite of its importance for many downstream tasks, the lack of relevant Amodal dataset with detailed annotations hinder explicit learning and modeling of intra-class occlusions. We built two Amodal datasets of density intra-class occlusion scenarios and provide detailed ground truth annotations of multiple types. For each instance, the annotation provides visible mask, invisible mask, Amodal mask that combines visible and invisible masks, complete appearance images, layer orders, and occlusion orders. The datasets can facilitate many applications, such as automatic harvesting, robotic stock building, and fruit quality control. Our new datasets are available to the novel and understudied problem of intra-class occlusion, unseen in previous Amodal datasets. Our two synthetic Amodal datasets contain a total of over 267,000 images of intra-class occlusion scenarios. Intra-class Amodal fruits dataset is built for intra-class occlusion of fruits and vegetables. Amodal common object datasets is built for intra-class occlusion of daily common objects. In addition, we built two datasets for testing the model's generalization ability in unseen scenarios, a real-world dataset of intra-class occlusions, and an inter-class Amodal dataset that considers the occlusion of multiple categories of objects. Our goal is to predict the Amodal mask and the layer order for all instances of a given image. During training, the inputs to our model are Amodal bounding box, the 10 annotation points for each instance rather than the full Amodal mask, and the layer order in which they are located. The layer priors allow the model to build separate representation for each layer, and thus capture intra-class occlusion efficiently. Our approach follows a two-stage instance segmentation method of detecting before segmenting. There are three major modules in our network: the backbone network, the region proposal network, and the cascade ROI heads. The cascade ROI heads include bounding box branches and mask branches. Then, we use point supervision strategy to make point predictions, and use subdivision mask rendering algorithm to refine instant mask with point prediction. As seen in tables, with the introduction of the layer priors, our weakly supervised method outperforms the best available methods on the intra-8-foot and acorn test set of intra-class occlusion scenes. Regarding the generalization ability test on the on-C inter-A-mix dataset, our mask performance is also optimal. Note that our method is able to simultaneously perform layer order bisection while being trained using only 10-point supervision. Our method also outperforms other methods by a large margin on the real image dataset, proving that our weakly supervised approach has great potential for generalization to real images, where annotation is expensive. Here is a visual comparison of the results on the two test images with heavy intra-class occlusion. In the top example, our method predicts more reliable Amodal bounding boxes and shapes for the two instances at the top of the image, despite the heavily occlusion between them. In the bottom example, our method predicts more reasonable shapes for the fully visible and partially occluded object in a realistic image. In summary, we present new datasets and a weakly supervised strategy to solve the novel problem of Amodal instance segmentation with heavy intra-class occlusion. Thank you for watching.